Hey, hi. Let's see. So the quiz this week is basically going to be calculations using this activity coefficient. Similar. It's going to be similar to the things we did last week, except that it using the activity coefficient with it, then you end up with these kind of more complicated routines that you need to do. So this is in this Appendix C in the back of the book. And it goes through how to use activity coefficients for different kinds of calculations, like for bubble temperature, dew pressure, dew temperature, flash calculations. And so that's kind of the goal of the chapter for the most part, though it has a bunch of other things in it, right? So the other chapters, it has some things just stuffed in. So if you look at the old quizzes, they're basically that kind of. So chapter 11, so 17, 19, 20, and then 2016, they're all more or less the same thing, you know. Calculate these, use the activity coefficients and calculate the bubble point, calculate the whatever. So basically, I'll go through today kind of how to do that, how to do those calculations. Tomorrow I'll do some problem sets. Maybe just go over the old quizzes. Is mostly what needs to be done. So the issue is that we have like Raoult's law would be the straight line where the pressure's proportional to the composition, and then you see these deviations, like a positive deviation from Raoult's law. So you want to be able to model that and be able to do calculations to calculate the bubble point pressure and the dew point pressure, right? And to do that, you need to use this activity coefficient. So last time I kind of gave a little bit of an overview, at least of the Margulis single parameter coefficient for this. Right? So you have basically from Boltzmann equation that the change in entropy is going to be proportional to log of the composition. You can think about that in terms of a probability if you want, or you can just accept the Boltzmann equation. And then if you have a mixture of two things, then you just do a mixing law to mix those log of x terms. And then since the Gibbs free energy is the enthalpy minus the entropy, T times the entropy, and do T times this, and you get the free energy if the delta H is 0. So an ideal mixing case is this XA log XA, XB log XB. So we got that in chapter 4. We kind of arrived at that expression. And then if you want to, and then for a real solution, so this kind of real solution model, right? Should be probably bold, but so you just add in a term. So you say you have binary interactions. So you get the probability of finding, like if you have a mixture of A's and B's, right? The probability of finding an A is a mole fraction A, and the probability of finding a B is a mole fraction of B. So the probability of a A-B interaction is XAB times X, the mole fraction A times the mole fraction B. And then you just take a constant and call it omega AB. That would be a Hildebrandt interaction parameter, or you can call it A12 would be the Margulis, would be X1, X2. And you can also call it the chi parameter for polymers. So this thing has different names where it came from different contexts. And Margulis is kind of an engineering term, and the Hildebrandt is more like chemical physics. and the chi is a polymer. But the expression is going to be the same. It's just the mole fractions. That's the probability of an AB interaction. This is for binary interactions. And you're just going to add that term to this ideal mixing term, which is just a rule of mixtures, x1, x2 times this Boltzmann entropy. Right, and this is divided by KT. So the entropic parts of this won't have a temperature in them because they have to be S times T to be entropy. That means this term has to be, A12 has to be 1 over temperature to account for the 1 over temperature over here. So that A12 has to be proportional to 1 over T in order for it to be an enthalpy. And it has to be, you want it to be an enthalpy. So the expression for A12 is going to involve 1 over T if you do a calculation of it. So A2 will change with temperature. A2 is a function of temperature, which kind of makes sense. You think the interactions will be impacted by temperature. Anyway, so basically, that's the expression we're going to be working with. So then all right, so the way this is looked at is this. You have delta G over KT, or if we're doing per mole, it would be over RT equals ln of x1, ln of x2. Those are the two entropies, and their mixing rule is that they go with x1, x2. Then you're going to add this binary interaction, x1, x2 times A12. Right, so another way to look at this, that's kind of a simple way, find the 1,2s and then multiply by some constant that's the average energy of interaction of 1,2s, which would be like the energy of 1,1 plus the energy of 2,2 minus 2 times the energy of 1,2, because that could be 1,2 or 2,1. And so there's going to be 2 of those. And then divide that by 2. That gives you kind of an average energy of interaction. And then you would have, like, if you had a model for this in a computer simulation, you'd have like 6 places where they could interact in a Cartesian coordinate. So you'd have like a Z number, which would be the coordination number. And then you divide that by KT, because this thing has to be inverse temperature dependent. And that would be kind of A12, be some function like that. So you can calculate this thing kind of for a computer simulation if you want. And then you'd go in and vary these energies to change how that thing would act. Okay, so this is amenable to computer simulations, like on a grid. Another way to look at this is to say this kind of probability. So you can think of this as a probability of, say, this is a probability of finding an A. Say, the mixture of A, B. The probability of finding an A is XA, which is like the number of A's divided by the total number of lattice sites that are taken by the components. If you said, like, how many arrangements could I make of A's in that? So the omega from the Boltzmann function is going to be like N over NA. So like that's how many ways A's can be arranged in the N lattice sites. Right. So this kind of delta S equals negative ln of X, or exponential of delta S over KT equals some probability, so XA. So you can think of this as like a probability of finding an A, and it's related to kind of the entropy, right, in an athermal system, so it doesn't have delta H. So anyway, so if you want to say, like, if you have this enthalpy n, and that probability isn't XA anymore. In other words, if the A's really want to cluster together with A's and the B's want to cluster with B's, then you're going to have a positive deviation from Raoult's law. And in that case, if they're clustering, you're going to have a value of positive, or a number bigger than 1 for A12. And then in that case, in that case, because of clustering, then XA isn't really the probability anymore. It's not a random system. So you have some other number, an activity, A, you say, would take the place of XA. And then instead of writing a second term here, you could just write the original mixing term, X1 ln of the activity plus X2 ln of the activity. So this, and that would give you the delta G over RT. Also, from this expression, you can see this is the ideal part, and this part is the excess. So this is the excess Gibbs of mixing by RT. So you can write the delta G excess of mixing per RT is this Helmholtz expression, or Margulis expression. Right, that's the excess free energy of mixing. And if you look at it in terms of this, so you'd want to kind of break up A1 too. So you could say, well, there's an A1 is an activity coefficient times X1. So I can still base it on my original model, and then I just have this activity coefficient. Okay, so then in that case, if I have log, so if I have ln of gamma 1 X1, that equals ln of X1 plus ln of gamma 1. So I can break this expression up into this original ideal mixing term, and then this other term, which will be look just like it. And instead of ideal mixing, it's going to have gamma 1 plus X2 ln gamma 2. And these are called the activity coefficients. So gamma equals the activity, the actual activity divided by the mole fraction, gamma 1. So things get kind of dicey here, right? So you have all these numbers showing up. So the activity coefficient and the Margulis coefficient are like two things that are somehow related to each other, right? So you want to know, how could I express the Margulis coefficient in terms of the activity coefficient? Or how can I express the activity coefficient in terms of the Margulis coefficient? So the way that works out is that ln of gamma 1 equals A12 times X2 squared, and ln of gamma 2 equals A12 times X1 squared. So the numbers swap here. Right? And the reason that comes out that way is this. So let's see here. So you have the intrinsic excess Gibbs energy. Right, it's going to be the sum of xi ln gamma I. That's this expression. That's the excess for this activity thing if the activity is gamma x1. Right, and then so that's per mole. Intrinsic means this is the Gibbs free energy per mole, the molar Gibbs free energy. Right, so the actual Gibbs free energy is that thing times n. So then Gibbs free energy per mole times n gives me the actual free energy. So this underscore is the excess actual free energy, not the molar free energy. So that's an extrinsic term, right? And if I want to know, so then the derivative of that actual value of the free energy with respect to the moles of one of the components, let's say component A, would be the chemical potential of component A. That's the definition of the chemical potential. It's also this GI bar, which is called the partial molar Gibbs free energy. So there's three kinds of Gibbs free energy here. Two of them are distinguished by bars, one's subscript and one's superscript. Right? So it's if you read the chapter, it's very important to figure that out. Okay. So this is intrinsic and means per mole. Right, that's the ones like in the table for steam table. Although Gibbs isn't given there, but the enthalpy would be per mole. And this is extrinsic, means it's the actual value for the system for the amount of material that you have. So it's this times number of moles in the system. And this UI is a derivative with respect to the number of moles of the component. Right, so this G. This derivative isn't the same as this thing. This is per total number of moles. So N is the total number of moles in the system of a mixture. And this is the derivative with respect to the specific number of moles of one component. So it has an I attached to it, naming the component. And that derivative is the chemical potential. This isn't the chemical potential, even though it's per mole. This is per mole, but it's per mole of that component. It's like taking that one component out of the mixture. How does the Gibbs free energy change? That's the chemical potential for that component in that phase. Right? The excess Gibbs free energy and for that component in whatever phase you're taking it out of. Right, so it's complicated, right? But this thing equals the log of the activity coefficient. That's the excess. The chemical potential is defined in terms of this activity coefficient. So this is an identity. So once you have that, then you can write in. Then you can do this derivative with this expression. So if you do that, you find that you had the molar Gibbs free energy is A12 times x1, x2. You need to multiply by n. And if you do this derivative, then you find out you're going to get two terms. One term would be the derivative of the first times the second. So you can re-express x1 as n1 by n, x2 is n2 by n. You multiply by n, you just have n2. You're going to do the derivative with respect to n1. So n2 doesn't depend on n1, that's just a prefactor. n1 depends on n1, so you end up with 1 over n1. And n depends on n1 because n1 plus n2. That ends up giving you n squared times n1 because it's the derivative of 1 over n and the derivative of n1 plus n2, which is just ends up giving you n1. Right, so anyway, you end up with this expression. The first term is n2 over n, which is x2. And the second expression, or you can pull that 1 over n out, and that's x2. Then you're left with 1 times n1 over n, which is 1 minus x1, which is also x2. x2 times x2 is x2 squared. So you get this relationship that I showed you before, this thing. Ln gamma 1 is a12 times x2 squared. So that the reason to go through that is that this thing you need to do this repeatedly to solve these problems. Okay, so it's kind of confusing. You don't necessarily need to understand. You just kind of need to know that these expressions have some kind of basis. You need this expression, these expressions, and probably this gamma expression, like this expression. Right, so it's kind of like three things you need to do to solve these problems. Right, so they're all of them are right there. Then this chapter has a ton of equations. I don't want to go through these right now. Basically, I just piled them all here, so it was a convenient place to find them if I need them. Some of these we already have, like the excess Gibbs is going to be this expression. The excess Gibbs is also this expression. This is a relationship between gamma and x and A12. And then this is how you can calculate, one way to calculate A12 using these parameters A12 alpha and beta from the back flap of the book, which I promised you we would someday use, right? So this is the day. So back here you have, at the last two, you have alpha and beta, right? That's the acidity, the basicity, and then you have rho, which is 1 over the specific volume, centimeter cubed per gram, and you have molecular weight. So you take molecular weight times divided by rho, you get the volume per mole. So these two numbers multiplied together give you this V1, V2 here, and the alphas and the betas. So if you have two components, you can look up their values and you can calculate for a given temperature. And you see there's the 1 over temperature dependence of A12. A12 is proportional to 1 over T. Right, so that makes it an enthalpy because it's going to be multiplied by RT. You know, when you include it to calculate the Gibbs free energy, it's basically, in order to be an enthalpy, it has to be independent of temperature when you calculate Gibbs free energy. So that means it has to have a 1 over RT because you divide it by RT here. So anyway, so that's a lot. So I'll show you this later. We'll do a problem using that. And then the fugacity shows up, its evil face here, and it's kind of a mess. And basically, we're going to skim over the fugacity part. because it's just too much, I think. And then you can also use this, you can get the K ratio and do distillation columns with this approach too. So we'll go through this in some detail in the chapter. There's more equations. So there's also a 2-parameter Margulis model that's based on the Redlich-Keister model. And then we'll go through this stuff too. And then what else is in here? The chapter at the end goes through 2 important things. One's osmotic pressure, and one is something else. I don't see it here, but there's 2 things at the end of the chapter we'll probably do next week, because it's too much to cover. But I think we can get through solving the problems for the quizzes today. And then go through examples, calculations tomorrow. So I think I've already kind of gone through this. So this is important. Okay, so this I haven't gone through. So let me get rid of that. So we have, let's see. So the K ratio, right? So we have the K ratio. So Ki is Yi Xi. So it's a split. It's how you split when you have a vapor, you have a liquid and a vapor, and it has an Xi composition of component X1 of component 1 and the mixture, then Y1 and the vapor, right? And what is the split? Like, how do they split? So Ki is Yi over Xi. And normally for Raoult's law, we said that thing was P sat I over the total pressure, right? But now because Xi, so we want the activity instead of Xi, and activity is Xi times gamma I, right? So this should be gamma Xi instead of Xi, but experimentally we know Xi, like how much did we shovel in to make the solution? That's Xi. We don't know alpha I, right? So we can put gamma I here, and then we can get that expression. It gives us the experimentally accessible numbers, the mole fraction, the solution, mole fraction of the vapor, the pressure that we can measure, Psat is a function of temperature, and then gamma I is the thing that makes it non-ideal. Right, so if gamma I is 1, that's Raoult's law. That's Raoult's law, gamma I is 1. Right, and we know that, so when does gamma I equal 1? We know that ln of gamma I, or gamma 1, equals A12 times x2 squared, right? So we can say gamma 1 equals exponential of A12 x2 squared, right? So when x2 is 0, in other words, when the one component is 100%, then this thing is exponential of 0 is 1. So gamma 1 equals 1 when x1 goes to 1, right? So we have kind of a way that we can reach this. So at the two limits, if we plot gamma I, right, and we have mole fraction 1, then we know that like one of the gammas is going to be 1 at one end and the other one's going to be 1 at the other end. Then they'll somehow vary through this, right? And then when when x2 is 1, right, then gamma I is exponential of A12. So over here it's A12 exponential, right? And over here it's exponential A12. So if you have a single component Margulis expression, depending on what the value, if A12 is smaller than 1, then this will be less than 1. So the value of A12 will decide if the gamma is bigger or smaller than 1. So you have positive or negative deviations from Raoult's law. That's the point, right? And if A12 is gives 1, exponential A12, then this thing is following Raoult's law. That's a straight 1 across. Right, so the way this is gamma I'm plotting here. This is gamma 1 and gamma 2. Anyway, the way this works out, these equations give you some answers, even just messing around with them. That's kind of the idea of this. So anyway, it's surprisingly complex for something that's commonly used. Like this is used everywhere for any kind of mixture, right? So this is like the most fundamental approach to this. So it seemed, but yet it's really complicated. But if you do some problems, you start to get used to it a little bit. You can at least solve, I guess the goal of the thing is just to be able to solve some of these problems using the activity coefficient, get a feel for the terms, and then hopefully you can go from there if you need to. My best to give you a basic background in this stuff. It's not necessarily to become expert in it. So if you aren't going to feel really comfortable with this when we're done, just don't expect to. Basically, you should get a feel for kind of what's going on. That's the idea. Anyway, so these are the same things. So this is just a rearrangement of this same equation. Like I said, y over x is gamma p sat over p. And if you rearrange it to get gamma, you get p sat times y, and p times x gives you what gamma is. It's the same equation somehow. Right? Maybe I wrote it wrong, but basically that's the same equation. That's the same. Like the p sat comes down here times x, and then the p goes up there times y, you get gamma. Right. So, and then what else is in here? So you can get, say, experimentally, you know, x and y and p sat for some point. You know the temperature, you can get p sat. You're given the pressure, and you're given the two compositions, you can calculate gamma. Right. And then once you have gamma, you can plug it in here and get the free energy excess. Right. Once you have that, you can get the free energy, you can get the chemical potential, so you can get a lot of things. Right. So here, that's basically what's said here. Experimentally, you're given the compositions of the vapor in the liquid, then you know the pressure, and you can get p sat from the temperature using the variety of methods we got in chapter 8 or something. Right. And then you can use that to calculate the Margulis coefficient. You can also calculate the excess Gibbs and the Gibbs from that. And then from that, you can calculate the bubble, dew, flash, whatever you want, any kind of thing. So, and the methods to do that are the methods I kind of flash by you. So it's all written out like the steps that you take to do this. It's going to be mostly iterative because there's two things you don't know. You don't know the gamma, and you don't know whatever it is you're trying to solve. So you have to iterate to solve these problems using an activity coefficient almost always. Right. So everything's going to involve iterations. Meaning solver in Excel, or you could use some other program to do it. These are the two main things for Margulis one parameter. We've already gone through those, right? So it's gamma 1 is x2 squared times a12. And then this excess Gibbs is a12, x1, x2. And that other expression for the log of the gammas, this expression, right? Log gammas times the rule of mixtures. So 11.1 is kind of simple. Like I think everything's given here. There's no iteration. So this is the only problem that you don't have to iterate, right? So it's like you're given some composition, the solution, the liquid composition, and then find the Margulis equation, data from the original citation. So it's given a temperature, so you can get p sat. So you use Anton equation or something else to get p sat. Like you could use the critical temperature and things if you wanted. So somehow you get p sat from the temperature. And then y1's given. So x1 and y1 are given. And then you know the total pressure. So you know y1, x1, you calculated p sat from Anton equation, you're given the pressure, then you can calculate the two gammas. Y2 is going to be 1 minus y1, x2 is 1 minus x1. P2 sat you get from Anton equation, P is the same between the two. So you can get the two gammas given the information that you gave. Once you have the two gammas, you can calculate the excess Gibbs, which I think is what the problem is, right? Calculate the excess Gibbs. So once you have the two gammas, you just plug and play, and you get the Gibbs, excess Gibbs from that. If you have the excess Gibbs and you know the two compositions, so x2 is 1 minus x1, you know x1, and you know the excess Gibbs, you can calculate what the a12 is for this case, although he doesn't ask for it. But so you can just solve this equation to get the excess get the Margulis single parameter. Turns out to be 1.42, so it's a positive deviation from the Raoult's law. And you can see in this plot, it's a positive deviation. Raoult's law is a straight line, and this deviation goes up. Right, so it's a positive deviation. It also has an azeotrope. So there's also this point where you can't distill past that point we mentioned last class. Right, so this is like the simplest thing you can do. You're given everything. Generally, you're not given everything, and you don't need to be given. This is over information. Like they've given you more information than you need to solve this. Right, and we'll see how to solve these things with less information. Let's see. So that's that. And then so if you plot this excess Gibbs though, so the experimental values for that same system, this is propanol and water. Okay, so you can see that one parameter. So once you have A12, you can calculate this Gibbs for that temperature. Like A12 is 1 over temperature. So this is a temperature dependent. You can plot this excess Gibbs as a function of composition. So that's a one parameter Margulis. So it's symmetric. That's the point. It's symmetric about 50%. It has to be because of the way this equation is written. So I can swap x1 and x2 and I'll get the same answer on opposite sides, like 25% and 75% have to have the same value. And they're both going to go to 0 at the limits, right? So it's symmetric, but the data isn't symmetric. That's because for this situation, to get a positive deviation, the propanol has to like propanol more than it likes water, and the water has to like water more than it likes propanol. And it turns out the water likes water more than the propanol likes propanol, and that makes it skewed over to one side, towards the water side. Right. So depending on the affinity of the components, like I said, like you're going to have this average energy of interactions, E11, E22 minus 2, E12 divided by 2. That's your average energy. So basically, these things can be different values. Like the 1,1, the propanol one is smaller than the water one, and that makes it skew over to the left like this. Right. So that's kind of why it's moving over. So you can't do this with a symmetric, you can't match it perfectly with a symmetric one parameter Margulis model. Although you can get an almost perfect match. In other words, this is plenty good to do almost all of your calculations. And adding another parameter is going to make your life a nightmare. Right. So you can do almost everything with the one parameter and it's good enough. Like you can predict the azeotrope. You can in the system, and you can basically do a lot of what you need to do with the one parameter, and it's really a pretty good match, right? Considering that it's one parameter, just one parameter you're using to do this. The two parameter can give a perfect fit, but it's going to be added baggage to carry around, so it'll really complicate things. You'll see, but possible to do. It isn't impossible, but. And then this Van Laer model is another approach. It doesn't work as well for the system. And then you can go to more parameters. You can add as many parameters as you want. You can do a power series, and I'll show you how to do that. That's a Redlit-Keister model, right, that you can put in more and more parameters. Anyway, so the strategy is get the gamma somehow with whatever information you have. And this could be iterative. So you might not know. You might know P, but you have to iterate this thing to get P right. Right. So you can calculate P is going to be the sum of Y's. So YI times P sat I plus Y2 times P sat 2, so say 1 is going to give you P. Right. That's our general rule. So P sat is going to depend on the temperature, but the Y's are going to might depend on something like you're trying to get Y from this equation, like you know X, and then you need gamma to get Y, but to get gamma, you need the P. So these things are all, what do they call it? Redundant, like they're redundant on each other. So you need to, not redundant, they're, can't remember the word, but they rely on each other. So basically, all the parameters you're using rely on each other, so you use iteration to solve it. And that's pretty common. We've already done that more or less. So that's the routine they're going to need for this. So this is a general thing. Like you're going to get gamma, you're going to use gamma to get the excess Gibbs. You're going to use excess Gibbs to calculate the number that you want for the equilibrium problem that you have. Right. So this is pretty well worked out. It's just a matter of using these routines. So for instance, like the bubble pressure, right? And we're using this modified Raoult's law because we have gamma in it. Right. So basically the bubble pressure is the simplest problem for these kind of things. We saw from last chapter, like the hardest is these adiabatic flash calculations. So the bubble pressure is the simplest. Is still, with this throwing in this monkey wrench, it's basically a little bit more complicated, and you have to do an iteration to solve it. Right, so you know you're given the solvent, the solution liquid composition, you know the temperature. So with the temperature, it gives you Psat. And then with the liquid composition, you need gamma to get the to solve the bubble pressure problem. You need gamma here. So the first iteration, you just say gamma is 1. You just say it follows Raoult's law. Then you can solve for y with x, because you know it's going to be Psat. It's going to be the Psat equation, like y over x is Psat over p times gamma. So if you assume gamma is 1, then you can get, you know Psat, you know p, then you can get y from x. You have x, Psat p, gamma, you assume 1, you can get y. Once you have y, you can calculate the bubble pressure, because the sum of y times Psat is going to equal 1. Right? So then you see if that's true or not. Then you go back and modify. Then once you have, well, sum of Psat is going to be p. And then once you have p, you can plug it in here, get the x. So you can iterate this thing back and forth. Right? So that's the routine that you're going to do. And you can do that in Excel, or you can do it in MATLAB if you want. We already did that. So that's example 2, I guess, here, right? Which is, I think, let's see, example 2, I don't think you need to iterate. Let's see. Yeah, that's not the one I want. Yeah, example 3, you have to iterate. Well, example 2 is just a calculation. It's use a fit of 11.1. So that gave a Margulis coefficient to predict the PXY diagram used for figure 9.5, which is used for figure 9.5. Where is that? I think it's this diagram, this PXY diagram for propanol water. At 30 degrees C, the data used for figure 9.5 show X1 and Y1 at P is 60 point whatever. So from this diagram, you have, so the data, we already have A12, the 142 came from 11.1, right? And then the composition, the composition 11.68 for X1, then X2 is going to be 1 minus that 88.32. So from the composition and the A12 from the other example, you can get the gammas. And then you're trying to show that show the y from that, calculate the y from that. So the y is just going to be so this is the bubble pressure calculation. So bubble pressure is going to be sum of y equals 1. So this is y, right? Some x1, gamma 1, p1 sat gives you y times p. And then the other one for 2 gives you y times p. You sum those up, you get the total pressure, which is 50.4. And then And then, what is this again? 462. Then once you have the pressure, you can calculate Y1 times P sat over P. Let's see, this is gamma 1. This is gamma 1. It should be gamma 1 times P sat over P should give Y1. Oops, let's see. That's the expression that should be. So, because this is gamma 1 P sat over P should give Y1 from this thing. So this should be gamma 1 P sat over P. And then gamma 1 P sat. So that's basically this thing, right? Y1 P over P gives Y1, right? So he's got this expression for Y1 P, and then divide by the P that he got here gives Y1 0.426, which doesn't agree with the 0.5316. So that's because this Margulis 1 parameter doesn't exactly fit the data perfectly, right? It's like missing at that, wherever this is. It's like not exactly right. We're at 0.3 something here, so it's a little bit off. X is 0.1, so at 0.1, like you don't expect them to match that well. So the experimental data point and the dashed line aren't exactly the same, right? So that's why they don't match up here. This one doesn't require iteration. 11.3 is kind of a more typical problem. So 11.3. Okay, so 11.3, you have propanol water forms an azeotrope. So let me shrink this. So you're given the azeotrope conditions, right? And at the azeotrope, so when you have the azeotrope, meaning this point where the things cross, so you're at this point where the two match up. And at that point, Y and X equal each other. Let's see if there's a plot of that. So when you're at, like if you're doing pressure versus composition, the X and the Y are the same at the azeotrope. That's why you can't separate anymore, because when you boil it, the vapor has the same composition as a liquid. So you can't do a separation. It doesn't have a higher content of the light components. So basically, if you're given the azeotrope, you know that Y equals X. If you're given X, that's the same as Y. That kind of simplifies things, right? So you want to know what's the Margulis parameter by fitting the bubble pressure of this composition at the azeotrope. You compare a result with Raoult's law approximation to the data that's given, where P equals given the pressure, and then so use that Margulis parameter to do a calculation of different conditions. So use the same Margulis parameter, same temperature, but different pressure. Right, so use that Margulis for some other conditions. So Margulis is going to depend on 1/T, but it doesn't depend on pressure. So it has to be the same temperature, but it can't be. You could adjust the temperature just by dividing by temperature in absolute units, right? If you wanted, if you have a Margulis, you could adjust it. Anyway, so to do this, this is how you do these. So basically, this one's going to be a solver routine, just a simple solver routine. So you want the pressure. It gives the hide this. So it gives the azeotrope at 760 millimeters mercury. So you have to have that that the pressure. You're gonna vary A1. You're gonna vary the value of A12 to get the pressure right here. So the pressure is going to be the sum of the P sat, so E11 or E14, right? The P sat times times the gamma times the x that you have feeding in, E9, E9, like these x's here. So it's x times gamma times p sat. X times gamma times p sat gives you y p sat. So y by x equals p sat gamma p sat over p. So yp equals x gamma p sat. Right, so if I sum up yp's, I get p, and that should be 760. So, and gamma is going to be, oops, wait. Sorry. So y by x is gamma p sat by p. So yp is x times gamma p sat. And the sum of these equals p. Right? And gamma is A12 times x. Like if it's gamma 1, it's times x2 squared. Right? So if I vary A12, I know the x's, I can get the gammas, I know the x's, I know the p sat from the temperature. Then I can get this calculation from knowns. All I have as a variable is A12. I can vary that until I get P to be 760. Right, so I do that just with solver. So that's what this guy does. Right, it's just set up. It's got the calculation. So A12 I'm varying. The gammas are the other component squared times A12 exponential, and then P is the sum of the two x p sat gamma to give total P. So I just do solver. I say want this to be 760, and then run the routine by varying the A12. Want it to be 760, and then the pressure, and then vary A12 to get it. So that just solves it for you. That gives you the answer, which is going to be the A12 values 1.368, 1.37. Remember before we got 1.41 from a single calculation with all the values were given. We got 1.41. So it's a little bit different doing it by this routine. The A12 is a little bit different. And then you can calculate the bubble pressure doing the sum of the pressures under this other condition he gives, 66 and 0.639 at the same temperature, and then he gets that's the bubble pressure. Right, so the other thing gave a bubble pressure of 48.6. So that's one example. I want to show one more example. I'm not sure I have time, but let's try to do it. So the other example is, this is just calculating that acid base. That's just a strict calculation, taking the numbers and plug them in to calculate the A12. So that's not that hard to do. This is just get the A12 using the acid base numbers from that table I showed you. This stuff you don't need to go through. That we already did. And this is the two parameter Margulis. So basically the Keister gives us series expansions. You have, this is like a Taylor series expansions. You have like the first order would be, looks a lot like the single parameter Margulis. So single parameter Margulis, C12 0, D12 0, and the others are all 0. And you just have B12, which is A12. Two parameter Margulis need two parameters. It's written this way. So you have, it's allowed to be skewed because it has two parameters. 2,1 goes with X1, 1,2 goes with X2. But the way this works out, the B12 isn't the same. So A21 is B12 plus C12, A21 is B12 minus C12, and D12 0. So if you can convert from the Keister to the two parameter Margulis. And if A21 equals A12, then you have the one parameter Margulis, because X1 plus X2 is 1. And then So anyway, this is the two parameter Margulis. That's just all there is to it. So if you have two parameters, you can solve for both of these parameters with one data point. Okay, you don't need two data points to get this way this works out. It's like ln gamma 1 is A1, A2, and ln gamma 2 is the same thing, right? You just reverse the numbers and you get these two expressions. And you get that by doing the same derivative that we did with the one parameter where we got just x2 squared. But here it's a little bit more complicated, right? And then, and you can rearrange these to solve for A12 in terms of gamma 1, in terms A21 in terms of gamma 2. So you have one point, you have gamma 1, gamma 2, x1, x2. You can solve for both of these parameters, right? And it gives, so one point will give you the kind of the skewedness of this thing. As long as x1 doesn't equal x2, then this thing falls apart. But basically, any normal point, you can solve for the two parameters in the Margulis. So 11.5 is an example of that. It gives the numbers, just calculate the A1, A21, A212 using those equations. So you can get the two, and you can use those two parameters to calculate the GE, and that matches like the data almost exactly. So in this case, it's taking the information from 0.6369, which is pretty close to the azeotrope condition. Right? It's kind of almost at the azeotrope, just a little bit off it. That's why it matches. It kind of matches that point perfectly, because that point was used to calculate the two parameters. So it's the same point that was used for the one parameter Margulis, which is symmetric, and this one's asymmetric because of these the skew terms in it. So anyway, this is calculated dew point, which is like the second most complicated. And this one you need to do the iterations to do. So this one is like this is how you set it up. So you're gonna have a series of calculations. The first time through, you're gonna say that the gammas are 1. So that's Raoult's law. G1, G2, or gamma 1, gamma 2. Then from the gammas being 1, and then you're given A21 and A12 are the two things we just calculated. So it's for the same system. And you don't have X1s in the first round. So this is going to be like rounds, and you're iterating until the thing comes out. So from the gammas, you can get the Y, or let's see, the Y's, this is a dew point, so the Y's are given, right? You're trying to calculate a dew point. So the Y's are fixed. They're fixed all the way through, right? Every iteration has the same Y's. So you have the gammas, then you can calculate the pressure using the gammas. And the pressure, you want to iterate until the pressure stops changing. So the pressure is going to be this equation. So it's going to be, let me see if we can blow that up. It's going to be, for the dew point, it's going to be sum of y's equals 1. So you're going to have, this expression works out for the dew point calculations given on that thing here. It's this thing right here, right? So basically, let's see if I can shrink that again, or just undo. So basically, you're going to calculate the pressure. You're going to calculate the y. The y's are given, then you're going to calculate the pressure from the first round through is from the y. The y divided by the vapor pressure. Vapor pressure is fixed. It's over here, G, right? So you have the saturated pressure. Then the y's give you the total pressure from that, from this equation. And then once you have the pressure, then you can calculate x. So x is going to be the saturated, the G term. So the saturated times gamma. And then this is y, D8 is going to be y, and then y times p, the p that you just calculated. And that gives you x. So then you can calculate x, the two x's the same way, or 1 minus the first x is the second x. A12 is fixed, And then gamma you calculate using gamma is this x squared. So it's a 2-parameter Margulis. So you say that x squared, that kind of complicated x squared equation for the gammas, that thing. And then once you do the gammas, then you can calculate pressure the same way. And then once you have the pressures, you just end up with the pressure, right? And you're trying to see if the previous pressure is the same as the first. So then once you have that cell set up, you just copy that and paste it and do another iteration. So it's using, from the previous one, it's using the pressure. And then from this one, from the pressure, it calculates X. And then it just calculates gammas, and then it calculates P. So you can see, just repeating that over and over again, you can see it converges. Like you get 51, then 50.7, 50.6, and then finally it's at 50.6, and it doesn't change any. To do kind of a couple extras, and then you have, that's the answer, 50.6, and then you have the pressure, you have the Y's fixed, and you have the X's. So then you can get, and you have the gamma. So you have all the information about the dew point then. All right, so it's got to be done iteratively because you have to calculate the gammas. The gammas are dependent on the X, and the X is dependent on the gammas. To do it iteratively, the first time you go through, you say gamma's 1. And then you just keep repeating it until it finds a solution. So that's kind of how you do iteration in Excel. If it's in linear programming, you just write a loop. So this is kind of a loop in Excel. These will all be solved in 2 or 3 kind of clicks of the loop. So that's about, we don't have any more time, so we got to quit there. But tomorrow, I guess I want to go through these other 2 examples. We'll be done with this business of this programming this thing. And then go through the quiz, because the quiz will be exactly the same thing. The quiz will be like doing these same 4 examples. So just go through those 2 and then go through quiz, which will be the same thing. Tomorrow, we should be able to do that. They're basically the same idea. Like you're going to have the same kind of iteration doing the other calculations. So it's just like set it up and then copy and paste, do the real things. So they'll end up being kind of the same. So anyway, why don't we quit there? Any questions, anything? It's a lot of stuff, but basically it's similar to the last chapter. It's like 1 level higher complication. So hopefully this is okay. All right, so I'm gonna quit there then, unless there's questions.